Hi, my name is Mustafa Yusuf, and I'm a solar engineer at Neighbor Power. Over the past 6 years, I've designed over 3 megawatts of solar capacity across Western Canada and trained many solar design professionals across the country. I'm going to be teaching a solar design course beginning in the spring of 2020, and I hope that you can join me. The course is intended for engineers and other solar design professionals who want to advance their analytical and design skills in solar PV and microgrids at large. More information about the course will be released in the next few weeks. In this video, I'm going to go over the basics of a PV generator, which is the basic building block of any PV system. Let's get started. We will begin by introducing the basic electrical model for a PV cell, which we will then use to derive the operating behavior of any kind of PV generator. We're going to look at combinations of PV generators and how they are impacted by current and voltage mismatch. We're also going to talk about efficiency and how to be able to calculate efficiencies of PV generators. We're also going to talk about loading, or how does the size of a load that we connect to a PV generator affect its performance. And finally, we will compare specifications of 2 commercial solar modules and check some of the assumptions that I have made during this video. So a solar cell in the dark is simply just a diode, but when we shine light on it, it conducts current in the reverse direction. We can model the current and voltage of a solar cell using what's called the single mechanism 3-parameter model. It's made up of a current source in parallel with a diode. The current source magnitude is determined by the light intensity on the cell, and the diode is mainly environmentally influenced by the cell's temperature. The diode clamps some of the current from the current source, and it also sets the cell's voltage. The 2 most important parameters of any kind of PV generator are its short circuit current and its open circuit voltage. These are the maximum current and voltage values a PV generator will put out under the same environmental conditions. Given they are maximal values, they are quite relevant to the design process, beginning from picking your balance of system all the way to fault analysis. So if there are 2 values that you ought to remember for a PV generator, it's short circuit current ISC and its open circuit voltage VOC. If we short, quote unquote, the terminals of a PV generator, so if we connect its positive and negative terminals together, the current that flows between the terminals is this maximum current, which is the short circuit current. And as you can see, because there's no way to apply a voltage across a load, power output is 0. On the other hand, if we don't connect anything to the terminals of a PV generator and measure the open circuit voltage, the voltage that we will read is the maximum voltage that we can derive from that PV generator. Notice that in the open state, there's no current flowing in a generator, and in the shorted state, the voltage across the generator is 0. So both these states have 0 outputs because one of either current or voltage is 0. So both the open and shorted states don't deliver any power. But near the short circuit current and open circuit voltage are current and voltage values that yield the maximum power. We're going to call those INP and VMP, and their product is maximum power, or PMP. PMP is also the namesake, PMP under standard conditions, that is. It's also the namesake of a PV generator, whether it's a module or array. So for example, if we are talking about a 400 kilowatt solar array, we can infer from that this solar array has a maximum power point of 400 kilowatts. And although you may not know what IMP and VMP are of this array, you do know that their product or their products will yield 400 kilowatts. So the IV curve is only true for a certain light intensity and temperature. Change those and you get a new IV curve. The more light that we shine on a module, the higher its short circuit current becomes. And we'll actually see later that short circuit current is directly proportional to light intensity. The more light we shine, the higher the open circuit voltage becomes as well, not as much as current, and overall, because the maximum power point is shifting away from the origin, shining more light increases a generator's capacity. No surprise there. Temperature also plays a considerable impact on PV performance. The warmer it is, the higher the short circuit current is going to be, but the much lower the voltage is going to be. And overall, at higher temperatures, the maximum power point shifts more to the left than it does upwards. Therefore, it is approaching the origin. Therefore, higher temperatures lead to lower outputs. So oftentimes when we're building PV systems, we have to combine several PV generators, and we can combine PV generators either in a series or parallel fashion. When we combine PV generators in series, they act as voltage sources. They can have as much voltage across them as they want insofar as their currents are equal. And if we just assume, just for the sake of the IV curve, that we connect n identical PV generators in series and they are under the same environmental conditions, then we short this string's output, we'll find that the short circuit current is actually the same as the short circuit current of any individual generator in the string. On the other hand, if we open the string and measure the open circuit voltage, we'll find that the open circuit voltage is actually now the sum of the open circuit voltage in the string. We can also combine in parallel, in which case PV generators act as current sources. Because they are in parallel, KVL tells us that they must have the same voltage across them. So as long as they have the same voltage across them, they can pump out as much current as they want. Again, for the sake of the IV curve, if we imagine that we connect n identical PV generators under the same environmental conditions in parallel, and we short their combined output, we'll find that their combined output now has their sum short circuit current. But if we open their combined output and measure the voltage, we'll find it's the same as any individual generator's open circuit voltage. Now you may have noticed I started talking about cells, and then I gave an example of an array, and then I talked about generators in general. And that's really just because of the modularity of PV systems. Just as we use cells to build and predict the performance of PV modules, we use modules to build and predict the performance of PV arrays. They are all PV generators, and the rules that we are describing apply to any subset of PV generator. So I could be talking about a cell, module, or an array. So now that we know how to combine in series and parallel, let's try to determine this module's open circuit voltage and short circuit current given the following configuration. This is actually what's called a split cell module, which is becoming more and more popular these days. With split cells, what we do is we split a cell in half, and instead of having just a single string of 60 or 72 cells, we have two strings of 60 or 72 cells. In this example, we have a split 60 cell. To find the open circuit voltage of the module, we have to find the open circuit voltage of either string, which is simply found by multiplying the open circuit voltage of each series connected cell with the number of cells we have in series, which yields about 40 volts. And for the short circuit current, we add the short circuit current capacity of all strings that we have in parallel, which yields 10 amps. And you may have noticed these are the nominal values for any 60 cell, whether it's a single string or a split cell. So let's talk more about the configuration of the split cell. So as I mentioned, in split cells, we take the same cells, we split them in half, and instead of having them in a single string of 60 or 72, we arrange them in two strings of 60 or 72. So what happens when we actually split a cell in half? Well, if we consider a cell that has a certain maximum power point voltage and a maximum power point current, and then we split it in half, it's going to have the same voltage profile, but half the current capacity. If we split it into n pieces, every n piece will still have the same voltage profile, but it will only have an nth of the current capacity. And if we sum up their total capacity, we'll find that it's the same as the cell that we began with. So it's 6 of one and half a dozen of the other. So what are the benefits of split cells? One of the benefits are they enjoy a lot lower conduction losses. This is a single string of 60 cells. As you can see, if you're going to connect everything in series, you need to run down, across, and then up, and so on and so forth. The point here being is you have to run the entire length of the module. In a split cell, strings are arranged in a top section and a bottom section. So the string is half long. But that's not the kicker. That's not actually why it has lower conduction losses. It has lower conduction losses because power is directly proportional to the square of current. And because we've halved the current, we have managed to reduce our losses by 75%. So if a single string module had conduction losses of, say, 1 watt, its split cell counterpart will have conduction losses of only 250 milliwatts. So that's great. We have 750 milliwatts more to go to the output, 750 watts more for the maximum power point. And because there are going to be less losses in the module, with losses which are converted into heat, the module will operate cooler, therefore its voltage performance will improve, boosting the power output even further. But having said that, if we're comparing two modules, so let's say we have two modules, both have the same capacity, so we have two modules, they're each 300 watts. One is a split cell, the other is not. Given that they have the same capacity, We know that the single string module has to have higher efficiency cells in order to make up for the losses that the split cell takes advantage of. So just bear that in mind. Conduction losses are already reflected in the namesake or in the capacity of the module that you're dealing with. The second benefit of split cell modules is their ability to handle shading better. Let's look at why. First, let's look at shading in a single string. Suppose that one PV generator is shaded, connected to others in series that are not. The shaded generator is going to have a much shorter IV curve. And because they're connected in series, it's going to impose its limited current capacity on the shaded generators, the ones that are connected in series. And this is actually why modules and substrings in a module are fitted with what are called bypass diodes. These are Schottky diodes that short any current that the module or the substring that it's shorting can't derive for itself. It's not the best solution given that diodes do incur quite a bit of power loss, but it's better than diminishing your entire string's capacity. So now let's talk about shading or mismatch in generators combined in parallel. Again, if we have one generator in parallel that's shaded, it's going to have a much shorter IV curve. But as we can see, because voltage is just not that sensitive to light intensity, the combined output can assume essentially the entire current capacity with no problem. And here we can see the IV curves of both graphs, and we can see that their combined output will essentially be their sum of their current capacity. Let's talk about what happens when we combine strings in parallel with different voltages. So if we have two generators in parallel and they have the same open circuit voltage, even if we do connect them together, nothing's going to happen. No current is going to flow between them because there's no voltage differential. But now let us suppose that we have generators in parallel, but one, because it's shaded, has a slightly lower voltage than the others in parallel. Well, what's going to happen? Once we connect them, because they have different voltages, current is going to start flowing between them. And to figure out what that current amount is and the open circuit voltage of the combined output, we have to go back to the IV curve. So as I said, once we connect them, because there's an open circuit voltage differential between them, they're going to have current running between them. That current is going to be somewhere in the middle. In this diagram, I'm just assuming it's 34 volts. To find out what it actually is, let's go back to the IV curve. And let's now extend it beyond the open circuit voltage such that we're extrapolating it from the maximum power point. So again, at an open circuit voltage, there's no current running through the module. At slightly to the left of the open circuit voltage, the module is acting like a generator. Now we can see that slightly on the right, it will act as a load. It will act actually as a diode. So one module will be operating on the left of its open circuit voltage as a generator, and the other will be operating on the right of its open circuit voltage as a load. And to find their settling point, all we have to do is flip one IV curve. In this example, I just flipped the shaded one, but I could have flipped the non-shaded one, because once I flip them, I'm going to get a point of intersection where their currents are equal but opposite in magnitude. And that is exactly what's going to happen. They're going to share a current, and that current value will correspond to their combined output's open circuit voltage. So for our shading experiments, we're going to use these two what are marketed as solar cells. We're going to connect them in series and in parallel and see how well they perform when one of them is shaded. I know these are not solar cells because they put out 3.6 volts and 100 milliamps, and a solar cell only puts out 0.5 to zero point 0.7 volts. And if you look carefully, you'll actually notice. So there's obviously two columns, and if you look carefully, you'll notice each column has eight really tiny solar cells. And given that solar cells have an open circuit voltage between 0.5 to zero point 0.7, I'm inclined to think these are two strings of 8. One string of 16 would mean that their open circuit voltage is really low, and if there are four strings of 4, it could mean that they're super efficient. We can actually find that out. So if I'm looking at two columns, which are actually two strings, covering one string, shading one string, should only drop the short circuit current by half. Okay, so let's test that. I have this guy shorted through my multimeter, and I have this light, which as you can see runs in parallel to the column. And let's put all of it in the light and see what our short circuit current is. I'm getting a short circuit current. Oh, let's focus the camera. They're of about 31 milliamps. And so, but if I just put, if I cover half of it and leave the other one under the light, I get a short circuit current of 13 milliamps, which is, about half. There, let's just make sure it's all under the light. That's about half. So I am definitely looking at two strings, but like I said, it could also be four strings of four. To test that, let's let's bring the solar cell in perpendicularly, and if it's four strings of four, that top left part of the column is essentially one generator, one combined parallel generator. So it should be able to put out its own current, but we get less than a milliamp. We get no current. So it's more than likely that this guy is two strings of eight, because shading only half of it still allows it to push out more or less half the amount of current. So we're going to do the same thing. We're going to do the same shading experiment, but we're going to treat these two guys as two solar PV generators, and we're going to connect them in series and parallel. But this time we're going to be measuring, we're going to be looking at current and voltage a lot more carefully, and we're also going to be looking at bypass diodes and see how they affect performance. Right now the two PV generators are in an open state, and we can see that the open circuit voltage is about 8 volts. If I pull one out, we can see that the voltage crashes to about a half. If I pull the other one out, it crashes to about 2 volts. And if I flip them, just to simulate dark conditions, the voltage, now it's almost zero, just above zero. So now let's look at the sensitivity of current to light. And the easiest way to really do this is just to short the module or short the generator that you're working with, and do exactly the same thing that we just did. So I'm going to short it. Okay, now obviously the voltage crashed to zero, or very close to, and we're seeing a short circuit current of about 20 milliamps. And if I can probably tune it just to get it a little bit higher. There, it's about 30 milliamps now. And because they're in series, KCL tells us that they must be sharing the same current. So we're only strong as our weakest link. So if I pull one cell out, there, current crashes to zero. If I flip one over, now it's really zero. It was a little bit before. Bring it back in. Try the other one. So current is much more sensitive to light intensity than voltage. Okay, so now I have the two generators in parallel, and right now they're an open circuit and their open circuit is about 4 volts. And now if I short them, voltage crashes, and my short circuit current is about 60 milliamps, which is double of what we saw previously, given that they're in parallel. If I pull one out, flip it on its head, you can see that the current crashes to about half, and that's because they're in parallel. Bring it back. So lower voltage, but double the current, or half the voltage and double the current for parallel configurations. And as you can see, they're much better at shading because voltage is not as sensitive to light intensity as current is. Okay, so we're back to a series configuration, but this time I have these LEDs across each generator, which are acting as bypass diodes. And the reason why I'm using LEDs is if they're working, we're going to see them light up. So the bypass diodes are there to short any negative voltage, or to really short any current that the cell that it's shorting can't derive for itself. Let's see if I can pull. So let's pull this blue one. Let's see what happens. Oh, LED turned on, which means it's conducting. And let's try with the other one. Oh, it worked on its own. And the more I bring it out, the brighter it shines because the more current's running through it. If I bring it back, they'll go dark. Pull the blue one out. So we know that the bypass diodes are working. And let's just do this again by looking at the current. The green line, which is the voltage, but the green line is the same zero line for the current. If I pull one out completely, we see it doesn't actually crash to zero anymore. Thank you, bypass diode, this guy. Now let's talk about standard conditions that we use to report PV performance. These are a full sun intensity of 1 kilowatt per meter squared, which is often referred to as a full sun intensity, and it's more or less a universal value. A cell temperature of 25 degrees Celsius, and then air mass of 1.5. Air mass relates to just how much atmosphere light has to travel through before getting to the surface or the generator. As you can imagine, the more atmosphere that light has to travel through, the more attenuation it's going to experience. Space has an air mass of 0, and locations in high latitudes and in winter time in general are going to experience higher air mass, because you can imagine the sun's a lot lower in the sky, therefore light has to travel a greater horizontal distance. It's important to keep in mind this has nothing to do with the amount of power that the module received. That's already determined by the full sun intensity. This is more to do with the spectrum that the spectrum of light received by the generator. Now let's talk about PV efficiency and how do we calculate PV efficiency of a generator. Efficiency, just like for any energy system, is a ratio of output power to input power. Keep in mind though that in the case of PV generators, the input power is directly proportional to the surface area of a generator. So if I have two PV generators under the same environmental conditions, and they're each putting out the same amount of power, and one is half the size of the other, I can tell right off the bat that it has double the efficiency. So just keep that in mind. So, like I said, a PV generator receives light at 1,000 watts per meter squared, some of which gets reflected, some of which gets converted into heat. For the sake of reporting PV efficiency, we assume that the module or the generator is at standard conditions, and we also assume that the generator is operating at the maximum power point. So it's operating at capacity. As you can see here, the current and voltage outputs are IMP and VMP. So to calculate the efficiency or the standard efficiency of a PV generator, really all you have to do is divide its namesake by 1,000 multiplied by its surface area, because its namesake is its output at STC and 1,000 is the light intensity at STC. So all you really have to figure out is the surface area of the generator that you're dealing with. And we'll see later that even those are nominal, so they're either approximately 1.7 or 2. So you don't have to reach for the data sheet if you know this very simple equation. Let's just take an example. We have a 300 watt module with these nominal dimensions for a 60 cell module, and we want to calculate its STC efficiency. Well, we already know its output at STC, that's 300 watts. Its input is 1650. Dividing those two, we get 18.2%. Much easier than Googling the datasheet. Let's suppose now we have 10 of these modules side by side, and we want to determine their efficiency. Well, this array is going to be called a 3 kilowatt array because it's made up of 10 300 watt modules. This 3 kilowatt array will have a standard input of 16.83 kilowatts. And if we divide that by 3 kilowatts, we get slightly less than what we calculated previously. And that's just only because now that we're going to be mounting these modules, we need a little bit of space between them for expansion and contraction, and also to host the clamps. And if you were to compare the efficiency of a module with the efficiency of the PV cells that it's made up of, you'll notice that it is also a little bit less, because PV cells also need some space between them and so on. So now let's talk about what happens to the capturing efficiency of a PV generator. So how efficiently does it capture light at light intensities beyond the full sun? You can see here from this datasheet for Canadian Solar 305 watt module datasheet that at full sun we get 10 amps. So at 1,000 watts we get 10 amps, at 800 we get 8, at 600 we get 6 amps. So there seems to be this direct proportional relationship between short circuit current and light intensity. And if we assume that voltage is constant, which is obviously not a bad assumption, I think you will agree, we can go a step further and say that the module's efficiency is constant for this entire light intensity. So again, we started off from the observation that the short circuit current is directly proportional to the light intensity. And if we just assume that the maximum power point remains in the same position just for the sake of this light intensity range, we can just quickly deduce that, okay, well, the module has a constant efficiency even as low as 200 watts per meter squared. And we will test if efficiency remains constant at very low values at the end of the video. We're going to shine an LED on a panel, so it's simulating very low light conditions, and by using the ratio of the short circuit current at standard conditions to the short circuit current under the LED, we will predict what would it be if it was constant, and we'll see what it actually is. So what happens, or how do we predict PV's performance beyond a cell temperature of 25 degrees Celsius? Lucky for us, module manufacturers give us linear temperature coefficients. So really all we have to do is multiply the temperature differential we have in mind by the coefficient that we have in mind. So let's just take a quick example. Suppose we have a solar array now with an open circuit voltage of 400 volts and a short circuit current of 30 amps and the following temperature coefficients. And we want to figure out, okay, what is this array's open circuit going to be at the coldest time of the year, which is going to be 45 degrees Celsius. All we do is multiply the temperature differential from 25 degrees Celsius by the coefficient, and in the case of voltage, we notice that the voltage will increase by a little bit more than a quarter, and in the case of the short circuit current, it will decrease by a slight 3%. So this is very important because you have to make sure that your entire balance of system, all your converters, are rated for whatever the PV generator is going to put out. So for our final topic, let's talk about load resistance, or specifically, how does the resistance of the load that we connect to a PV generator affect the generator's performance? Now, as we mentioned, a PV generator has a maximum power point, and this maximum power point corresponds to a maximum power point voltage and a maximum power point current. You can reduce these two facts by saying that in order for the module to operate at capacity, the load must appear to have a resistance equal to its maximum power point resistance, which is just VMP over IMP. Or if you don't want to remember many numbers like myself, you can get away with approximating it using the open circuit voltage and the short circuit current. You can see the relative position of this approximation, and in our final slide we'll look at just how good this approximation is. So if we wanted to extract maximum power, we need that maximum resistance, and anything too low or too high from that maximum power point resistance will cause the module to look like it's opened or like it's shorted. And by that I mean, if it's looking like it's opened, its voltage is going to be very close to its open circuit voltage, and if it's shorted, its current is going to look very much like its short circuit current. Of course, it can't be exactly equal, otherwise the generator would be in opened or shorted states. But if they are really far, you can usually just make that assumption. And final thing to bear in mind is RMP actually doesn't behave like a regular resistor, so it doesn't intersect with the origin. The more light or less light that you shine on it, it's going to travel in a more or less a vertical direction. So first, let's look at what happens when we connect a very large load to our module. Remember that a very large load, that is one that consumes a lot of power, has a very low resistance. And a very small load, that is one that doesn't consume a lot of power, has a very high resistance. So with this module that has an open circuit voltage of 50 volts and a short circuit current of 10 amps, its maximum power point resistance is 5 ohms. And since we're connecting a 0.5 ohm resistance to it, it's going to look like it's shorted. So the module will be putting out a little bit less than the short circuit current. Here I'm just going to assume that it's equal to the short circuit current, and we'll see in the final slide just how good that assumption is. So if it's pushing out its short circuit current using Ohm's law, we can determine that the module will have 5 volts across it, which is also the voltage across the heater or the heating element. Therefore, the module is only putting out 50 watts, which is too bad because the module is actually capable of 400 watts. It's at STC. The module is capable of 400 watts. All we have to do is just dial that heater down, which may seem counterintuitive. So right now the heater is at a very high setting. What we actually do is bring it down to a medium or a low setting. And the reason being is doing that will get the heater's resistance closer to 5 ohms, which will allow the module to put out 400 watts. Now let's suppose we dialed it down way too far. We dialed it down such that now the resistance is 20 ohms. Now the module is going to look like it's opened. By that I mean its voltage is going to be slightly less than the open circuit voltage. So again, if we just assume it's the open circuit voltage, using Ohm's law again, the module can be putting out 2 amps. Using V squared over R or I squared R, the module will be putting out 100 watts, which is still only 25% of capacity. And this assumption that let's just assume it's the open circuit voltage is not as good in this case. And if you want a better estimate, all you really have to do is do a linear fit between the maximum power point and the open circuit voltage, or the short circuit current if you wanted to do it for current, and find where that linear fit intersects with your ohmic load. So that's all there is to it. So now let's say we finally tuned down the heater. Now the heater has a resistance of 5 ohms, which is equal to the maximum power point resistance. So everything's great, the module's putting out 400 watts and it's feeding our heater. But now let us suppose that light intensity has dropped by 50%. Does the module still operate at its maximum power point? And how much power is it putting out? Well, as we described, the short circuit current is directly proportional to the light intensity. So if we are getting half the light intensity, our short circuit current will drop by 50%. First thing we do is we sketch the new IV curve. We don't have to worry about voltage at all because we're on the shorted side, as you can see, of the IV curve. So light intensity dropped by 50%, short circuit current dropped by 50%. Again, because the module is acting like it's shorted, the load assumes the entire short circuit current. And I'm going to keep everything here symbolic so you can see the big picture. So the module is assuming the full short circuit current, which is 50% of the short circuit current at STC. Doing an I squared R on that, and if you just let me cancel the one IC with YMP, we can see that the power has dropped by 75%, although light intensity only dropped by 50%. So this just emphasizes that you need to actively tune a load such that the module appears to have maximum power point resistance. For our final loading experiment, I'm going to be using this 25 watt solar module. It's actually made up of 36 cells connected in series. At standard conditions, it has an open circuit voltage of 22 volts and a short circuit current of 1.6 amps. But under my LED, so under these low light conditions, it's going to have a short circuit current of only 85 milliamps. So if it is true that the efficiency of the module is constant even at a 20th of the light intensity, then we should expect to have a maximum power point at this low light intensity of only 1.3 watts. And we're going to find if this is true. We're going to scan an IV curve with our motor, and we're going to see if we can find a maximum power point that's close to 1.3 watts. For the variable load, I'm going to use this motor. This is my favorite hobby motor because it has a very low wide voltage range, and given that it has a higher gear ratio, it's capable of a lot of torque. To simulate a larger load, I'll be pressing down on the gears of the motor. That way I'll use that to shift closer to the maximum power point. And to measure current and voltage, I'll be using my Mushi meter. I'll connect the current meter in series with a PV generator. And the reason why I'm connecting the current meter in series with a PV generator and not the load is because I will have a capacitor across the load, and I don't want to be measuring any AC current from it. Okay, so I have everything set up. Let's go and turn the light on. Without the light on, the voltage is about 7.5 volts. When we turn it on, the open circuit voltage is about 19 volts. The motor is not connected, so this is the open circuit voltage of the module. Let's go ahead and connect the module. Let's go ahead and connect the motor, the load. As you can see, the voltage only dropped by about a volt. So the module is acting like it's opened, very close to the open circuit voltage. It's drawing about 30 milliamps, and right now the motor is consuming about half a watt. So now when I press down on the gears, So now when I press down on the gears, can see the voltage is dropping, but the current is rising much faster. Therefore, the power is increasing. Voltage is dropping, current is increasing, and power is rising. And about 1 watt. And if I press any harder, so it seems like maximum power at this point is about 1 watt. So if efficiency was the same as it is in standard conditions as it is at this low light intensity, we would have found a maximum power output of 1.3 watts, but we only found 1.1. Therefore, we can suggest that the module is 85% less efficient at capturing light at this low sunlight intensity. So I learned something interesting about motors, which I should have recalled from my first year, and it is about how we can generate the same amount of power using two different sets of current and voltage. So this is the IV curve, and these power contours that I drew are equal power contours. So any point that they identify, the power is equal. If one point has high current and low voltage, the other point has low voltage and high current. This is true for all points on the IV curve except for the maximum power point. If we multiply each point in the IV curves I and V and plot that against V, we'll get what's called the PV curve. Now it's very clear to see why any amount of power on the left or the right of the maximum power point can be derived by two different combinations of current and voltage except the maximum power point. That single combination we know is IMP and VMP. So what does this mean for a motor? Because the motor, as you may remember, started off at half a watt, and then I found the maximum power at 1 watt, and then when I pressed even harder, I found half a watt again. So what does this mean? How can a motor consume the same amount of power using two different sets of current and voltage? And what I figured out was because power in a motor is a product of torque times angular velocity, what was happening is on the open side, so on the side that had high voltage, I was running a very high RPM and low torque. And I know that because it was very easy to slow down the motor. On the other side, when I was pressing really hard on the motor, it was running very slowly. But I know it had a lot of torque because it was very hard to slow it down. So I thought of sharing that and segueing it with the PV curve. So for our final slide, we'll compare two commercial solar modules to check some of the assumptions that I have made during this video. The first module that we'll bring out is by LG. It has a rating of 365 watts, but it's only packaged in a 60 cell module. So it has super high efficiency of 21%. We're going to compare it with a module from Canadian Solar that pretty much has the same capacity, slightly less, but it's 14% larger. This one is in a 72 cell module. It's actually a split 72 cell module. It's 14% larger or 14% less efficient, however you want to look at it. It has 20% more cells in series. And if we divide the number of cells that we have in series in each module, or if we divide the open circuit voltage of each module by the number of cells that it has in series, we get an indication of the voltage performance of those cells in each module. If we divide the short circuit current capacity of each module by its surface area, we get an indication of its current performance, and that is again because current is an extrinsic value. It all depends on how much surface area the module has. And as I mentioned, the LG is super efficient, which makes it super expensive. It's actually almost double the cost of the Canadian Solar, which is why the Canadian Solar is much more popular. There is an exponential relationship between efficiency and cost per watt, and that is why at very high efficiencies, module pricing gets much and much higher. Now in the bottom, I've included some ratios which may allow you to get away not having to remember many individual specifications. For example, I've included the margin between the open circuit voltage and the maximum power point voltage, and you can see that despite that these two modules have very different efficiencies and configurations, these ratios are very similar. For in the case of the margin between the maximal voltage and the maximum power voltage, it's about 15%. The margin between the maximal current and the maximum power point current is under 10%. The third ratio is the resistance based on maximum power divided by the ratio based on the maximal values. And we can see the maximal values do yield a higher resistance, which is about 10% higher. And finally, we have the fill factor, which is your rating divided by the product of your maximal values. And as you can see, that's identical for both these modules, despite them being very different. For example, knowing that the fill factor is about 80% and just knowing a module's open circuit voltage and short circuit current, I can estimate that its capacity at standard conditions is going to be just 80% less of the product of the short circuit current and the open circuit voltage. Thank you so much for watching the video. I really hope that you've enjoyed it and that you've learned something. Please leave me a comment below if you have any questions or comments. And please subscribe to our channel to watch more videos and to learn more about our advanced design course that will begin in the spring of 2020. Have a great day.